Last time we were looking at titrations and what they are, and now we're going to look at the pH at various stages of a titration. The easiest one is the strong acid, strong base scenario, and that's because none of our products or the resulting salt of a neutralization acid, such as the one between nitric acid and sodium hydroxide, which are both strong, and that's for you to recognize. I may not tell you that that's what it is. I'm just going to say, hey, a sample of 0.2 molar sodium hydroxide was titrated with 2 molar nitric acid. You need to recognize that both of those are strong and that we produce sodium nitrate and water in this neutralization reaction, and that our resulting salt does not act as an acid or a base. So that makes our calculations of pH pretty simple. Here we have 50 milliliters of a 0.2 molar solution of sodium hydroxide, and if we calculate the number of moles present, so 50.0 milliliters times 0.200 moles per liter. I'm actually not going to convert the milliliters to liters. I'm going to keep it, which will give me 10, and then look at what cancels here. The mole doesn't cancel, but the liter cancels, but the prefix doesn't. That's just a milli, so the unit is still correctly canceled, except this is a prefix, so I'm just going to call that millimoles. Now, you don't have to do that. You can convert that to liters. It is not really a big deal because it's just going to be 0.0550, and then just like you move the decimal over here by 3, it would also then just be 0.010 moles. But as I said, you don't need to convert that because we're going back to molarity, and so we can keep everything in millimoles, right? So this is the number of millimoles of strong base before titration. And now I'm going to do the same thing with the 30 milliliters of the strong base. So I'm going to have 30 acid, 30 milliliters, also times 0.200 moles per liter, and that gives me 6 millimoles of strong acid, HNO3. I know all 6 millimoles are going to neutralize 6 millimoles of base, which means after 30 milliliters I still have 3 millimoles of acid left over. I also know that the total volume now is 80 milliliters, and so all I have to do is take the 4 millimoles of, and this is not H+, right? This is OH, because it's the base that's there in excess, and I'm subtracting the nitric acid, so I still have hydroxide left over, which is now in 80 milliliters. You see, now my prefix cancels and my units are moles per liter, which is molarity. So this gives me a hydroxide concentration of 0.05 m. So this is our hydroxide concentration, and the negative log of the hydroxide concentration will give me the POH. So the negative log of 0.05 m equals 1.3. Again, that is the POH. The question is for the pH here. So we do 14 minus 1.3, which gives me a pH of 12.7. As expected, something larger than 7, because we are not at the end point, we are not neutralized. No, at the end point, or the so-called equivalence point, we have now added 10 millimoles of base, so we've added another 50 milliliters of 0.2 molar, and at that point we don't have an acid or a base, so we don't have to calculate that. It's simply the pH is going to be equal to 7. And that is only true because we are using a strong acid and a strong, so the nitric is the base, is the acid and not the base. So strong, strong. So the pH at the end point or equivalence point is going to be equal to 7. Okay, so this is again just worked out. It tells you, I did this little calculation here. You don't really need to do this ICE table unless it helps you somehow calculate the number of moles. And but anyway, let's take a look at a different problem. Here we have a 40 milliliter sample of 0.1 molar solution of nitrous acid. Note that there's a huge difference between nitrate and nitrite. Nitrite is actually the conjugate base of a weak acid. So this is a weak acid, so we need to be careful here. We are titrating with a strong base, so we potentially have at the end point or at any stage we will have to potentially consider the amount of nitrite, which can of course react with water to form some of the nitrous acid back, and hydroxide, and that's going to affect the pH, especially at the halfway point or at any end point, halfway point, or at any time. So calculate, first of all, we need to calculate the volume required to reach the equivalence point. So here we don't have to worry about strong or weak. We just need to calculate the exact number of acid to neutralize the base. Okay, so if we have 40 milliliters of our acid and it's 0.100 m of the acid, that gives me 4 millimoles of acid. And so I now need to calculate how many milliliters of this concentration of the base we need. So we need also 4 millimoles and times 1 liter for every 0.200 moles of base. So moles cancels, the milli carries over, so we get back to milliliters, and that is 20 milliliters of potassium hydroxide. So we answered the first question. 20 milliliters of potassium hydroxide would contain the exact number of moles of acid, and that would be the neutralization point. Now they want us to calculate the pH after adding 5 milliliters of potassium hydroxide. So we already know that we have 4 millimoles of acid, and so this is going to be depleted, and so this is going to go down by something, but whatever it is shifted by is going to produce the nitrite ion. So we can actually use the Henderson-Hasselbalch equation. We can just simply say that the pH equals the pKa plus the log of our base concentration at equilibrium. So after it shifts, we need to determine that, and then plug in what is left over of the acid, and that is the HNO2. So we need to calculate the number of moles of base added, and so 5 milliliters times 0.200 m will give me the number of millimoles, and that is 1 millimole. So our acid goes from 4 minus 1, right, to 3 millimoles. So the pKa, by the way, you can look that up, is 3.24, and now we're going to add the log, and so we know that there are 3 moles, and technically I have to put in the molarity, so like 3 times 10 to the minus 3 but the ratio, whether it's number of moles or molarity, it doesn't matter. That ratio is still the same. And so we know that if we add 1 millimole of base, we're going to produce 1 millimole of conjugate base. All right, so this is 1. So therefore we get a conjugate, a pH of 2.76. This is 1/3. The log of 1/3 is like 0.4 something, and that's how we get the pH of that solution. At the halfway point, that means we have equal amounts of conjugate acid and base. The pH is simply equal to the pKa. Been through this, done this, no problem, which is 3.24. Here is everything worked out for you. And here I'm actually using molarities rather than or actually those are the number of moles, not molarities. They're the number of moles, but I convert to liters just in case you have some problems with that. Okay, so you can use ice tables. And okay, so this is the end of the buffer part. There's only one last little lecture about something called the solubility product. We'll do that next, and hopefully that'll be our final like 10 to 15 minute lecture.